Hi guys, and welcome back to my channel. In this video we'll be going over the rigid rotor model of a diatomic molecule and also be talking about microwave spectroscopy, which goes hand in hand with the rigid rotor model. Basically, when we're talking about a rigid rotor, we're talking about a rotation. So this is also known as basically rotational spectroscopy. Spectroscopy. So we've talked sort of about electronic spectroscopy, and we've looked at vibrational spectroscopy, and now we're going to look at not only exciting the electronic energy levels and the vibrational energy levels, but also the third and final rotational energy levels. So let's just get into it. So just as a review, I wanted to go over the other types of spectroscopy we've seen in the past. So electronic spectroscopy we've seen before, and we saw how we can use spectral lines to discern electronic energy levels in hydrogen atoms and other atoms. So specifically for the hydrogen atom, we looked at the Balmer series and the Lyman series and these different absorption patterns that you see in this spectrum. And these spectral lines are basically where electrons are absorbing certain frequencies of light, and they're jumping up or down their electronic energy levels. When they're jumping up, they're absorbing these frequencies. When they're jumping down, they're emitting these frequencies. And we can sort of see what the electronic energy levels are based on what frequencies of light the electrons are absorbing. Next, we talked about vibrational spectroscopy, and we saw how bonds have a characteristic absorption to excite to higher vibrational energies. So we saw that bonds will absorb a certain frequency that's equal to their characteristic frequency. And this characteristic frequency is based on both the reduced mass of the atoms and the strength of the bond. So we talked about that before. And we also talked about how we can apply this vibrational spectroscopy to zero-point energies and the kinetic isotope effect. So some use of vibrational spectroscopy. Now we're going to look at the next type of spectroscopy, which is rotational spectroscopy. So we've talked about electronic energy levels, vibrational energy levels. Now we're going to look at rotational energy levels. So rotational spectroscopy is basically how can we excite bonds to get them to rotate and excite them into higher energy rotational energy levels. Just as a review, I wanted to also mention that we know electronic spectroscopy generally happens in the UV and visible light range. Like with the Balmer series, this is all visible light, and the Lyman series is generally UV. So a lot of the electronic spectroscopy is in the UV and visible light range. Vibrational spectroscopy, exciting the vibrations of bonds like harmonic oscillators, will happen more in the IR range of the electromagnetic spectrum. And a really huge use of vibrational spectroscopy is called IR spectroscopy. And we see this in organic chemistry. We use IR spectroscopy a lot in order to figure out what functional groups are in a compound. And now we're going to look at rotational spectroscopy, and rotational spectroscopy happens more in the microwave region of the electromagnetic spectrum. So we can see how basically by looking at different parts of the electromagnetic spectrum, we can get different information on a bond, on the atoms in a bond, right? We can probe electronic energy levels with UV, and with visible, we can probe vibrational with a different frequency, and we can probe rotational with a whole different frequency. So we can see how we can get all this information out by using different frequencies of light. So now I want to talk about rotational spectroscopy, and say we have a diatomic molecule, AB. This molecule can only rotate with certain quantized energy. So this is the same sort of theme we're going with, right? Just like how we said, there's only certain vibrational energy levels, there's only certain electronic energy levels. Again, with the rotation, there's only certain rotational energy levels. And what are the rotational energy levels given by? We have E sub j is equal to h squared Planck's constant squared over 8 pi squared mu r squared times j plus 1. So this is a really kind of complicated expression, and it's definitely not in your best interest to memorize this. What we're going to do is see how we can interpret this equation and use this equation to solve cool problems. So this is our equation here, and mu is our reduced mass, and r is our bond length. So this gives us like something really interesting, right? We use bond length in this equation, right? So maybe by probing the certain frequencies that are absorbed to excite rotational energy levels, maybe we can tell something about the length of the bond. And this kind of makes sense, right? The bond length has to do with the rotation. Why? Because if it's a longer bond, if we want to think about moment of inertia, right? It's harder to rotate something that's longer than it is to rotate something that's shorter. So this sort of makes sense that it would be used, right? That we would have bond length in this expression. The energy levels for rotation should have something to do with the bond length because the bond length affects how easy it is to rotate something. Okay, so just some interpretations of this energy level equation. The minimum energy to excite a molecule into rotation, right, the delta E, to go from E1 from E0, so E1 minus E0 is h squared over 4 pi squared mu r squared. This is just comes straight from this expression when you take E1 and subtract E0. A really important thing I want to look at with this expression, right, with the energy level expression, is that you can see there's no 0 point energy, right? If we plug in E sub 0, right, J is allowed to be 0. If we plug in E sub 0, what do we get? We get h squared over 8 pi squared mu r squared, but then we multiply that by J and J plus 1. Since J is 0, we just get 0. So there is no sort of minimum energy, there is no 0 point energy when we're looking at rotational spectroscopy. That's sort of a really interesting idea because there was 0 point energies when we looked at vibrational and electronic energy levels. This is just another interpretation from that same expression. If we're going from the energy level J to J plus 1, so moving up in energy level, a rotational energy level, then our expression that we get is here, h squared over 4 pi squared mu r squared times J plus 1. And that just gotten from taking the E sub J plus 1, subtracting off E sub J, and that's the expression you end up with. So how can we use this to determine bond length? I sort of hinted at this before, but how do we use this to determine bond length, right? So say we pass a beam of microwave radiation. Remember, microwave radiation is what excites these rotational energy levels. So if we want to focus on rotation, we want to use microwave radiation. So we take this beam of microwave radiation and pass it through a gaseous sample of this molecule. So these increases in rotational energy levels will correspond to microwave radiation, which is what I said, but also, right, these frequencies that are absorbed are going to be used to determine bond length. So when we see a dip in the spectrum, right, when we see that a certain frequency is being absorbed, we know that that corresponds to some increase in energy level, and we can use that information. We can use what was absorbed to determine the bond lengths. So how exactly do we do that? Here's one way we can do that. The lowest energy absorbed, right, if we look at the lowest energy absorbed, that's going to be from J equals 0 to J equals 1. Why is that? Because remember, the energy difference, E from J to J plus 1, is proportional to J plus 1, right? So as your starting thing, or as the energy level you start at increases, it's going to become more and more energy intensive to go up in energy level. So the lowest energy that is absorbed is going to be the first excitement, the J equals 0 to J plus 1. And if we just set that expression that we got before, h squared over 4 pi squared mu r squared, which is the expression for when we go from E of 0 to 1, and we set that equal to the energy of a photon, we can solve for our bond length, right? We can solve for R. So just by rearranging this expression, we can get R equals square root of Planck's constant over 4 pi squared mu times the frequency that was absorbed. So again, this is one way to look at it, but if we know the masses of the two atoms, we can find the reduced mass, and if we know the frequency that's being absorbed, we can determine the bond length. And now we're just going to look at a really cool sort of problem that applies this idea of how we can use rotational spectroscopy to determine bond lengths. Okay, so how can we find the bond length of carbon monoxide? So carbon monoxide looks like this. It looks like a triple bond between our carbon and our oxygen, and that's the Lewis structure. So we know carbon monoxide has a triple bond, right? So it's a really strong bond, and it's a really small length bond. So that sort of should get us thinking. We sort of know that it's a small bond length because it's really strong. It's a triple bond. So we should know, like, generally what we're looking for. We should think about what this molecule is, what this diatomic molecule is, before we start deriving it. Now I want to look at this graph, right? This is a really important graph. We're passing microwave radiation, and we're figuring out what the transmittance is. So here is our microwave radiation on the x-axis, right? Our frequency on the x-axis, and we're looking at how much is transmitted. So what is transmittance? That's the opposite of absorption. Absorption is how much is being absorbed. Transmittance is how much is just going through and not being absorbed. So the dips in transmittance means a peak in absorption. So all of these dips are basically the frequencies that are being absorbed. What else do we see from this graph? We see that the dips are approximately the same distance apart, right? Like if I look at this dip, if I look at j to j plus 1 that I've labeled here, to j plus 1 to j plus 2, so if I look at this distance, that's basically the same as this next distance, which is basically the same as this next distance, and so on and so forth, right? So we see that these distances between the absorptions are basically the same. So maybe that's something to look for. Maybe that distance is key, and that actually is what is important to determining the bond length. So let's just look at the derivation. Each trough is corresponding to an absorption for E sub j to j plus 1, right? Each trough is corresponding to an increase in the rotational energy level by 1. So we got this formula before. We got that delta E when I'm looking from j to j plus 1 is equal to h squared over 4 pi squared mu r squared times j plus 1. And what does that mean about our frequency absorbed? This is the delta E, but remember that our frequency absorbed, when we have a photon, right, if we set this equal to h times our photon frequency, which is the energy of a photon, then we can solve for the photon absorbed just by dividing by Planck's constant. So we get that the photon absorbed, the frequency of the photon absorbed, is equal to h over 4 pi squared mu r squared times j plus 1. So this is important, right? Our photon frequency that is absorbed is this equation, that expression. Now I want to look at the distances between the troughs. So this photon frequency is corresponding to each of these on the x-axis, each of these dips on the x-axis, right? But I want to look at what is the difference between these dips rather than what is the dip itself, right? So now let's look at, instead of looking at the frequency absorbed, let's look at the delta of the frequency absorbed, right? So this is what we're going to do. We're going to look at between j and j plus 1, say, look at if we have this drop is corresponding to a j to j plus 1 energy increase. But the next drop is corresponding to j plus 1 to j plus 2. So if I look at this frequency absorbed for j to j plus 1, I get frequency absorbed, j to j plus 1 will get me h over 4 pi squared mu r squared, and I plug in the beginning energy level, j plus 1, right? Because I plug in the beginning energy level, which is j, so that ends up being j plus 1. But my next frequency absorbed, right, when I go j plus 1 to j plus 2, what does that get me? H over 4 pi squared mu r squared, but now I'm plugging in j plus 1. So that gets me j plus 2, right? So now if I subtract these two, because I'm looking at the delta between these two, I want to take my j plus 1 to j plus 2 frequency and subtract from that my j to j plus 1 frequency. So I'm going to take these two and find the difference between them, and the difference between them which is what I've written here. The difference between them, it corresponds to h over 4 pi squared mu r squared. And you can see that pretty easily. This one's j plus 2, this one's j plus 1, so if you subtract them, you just get this term. Okay, so now we have this delta. And notice that j is not in this expression, right? J is not in that expression, which makes perfect sense, because no matter what the J absorption is, right, no matter what all of these differences look basically the same. No matter which J it is, right, no matter if it's J plus 1 to J plus 2, or J to J plus 1, or J plus 2 to J plus 3, and whatnot, they all have basically the same difference, so there shouldn't be any dependence on J. Okay, so now we're going to use this expression, right, our delta of our frequency absorbed, to actually solve for the bond radius. Okay, so we have our delta of our frequency absorbed, and we can see from the graph, we can look at the graph and calculate what figure out what the delta is. And then we can solve this expression for r, which is our bond length. So if we just move that equation around, we get this expression, r equals square root Planck's constant over 4 pi squared mu times our delta frequency. If we just plug and chug then, we'll get that our bond radius, our bond length, is 103 picometers, which is actually exactly the length of the CO bond in carbon monoxide. This is a really cool application of rigid rotor and microwave spectroscopy, and using rotation in a way that actually gets you useful information. This is basically all I wanted to cover today. I hope this was informative. Thank you guys so much for watching, and I'll see you in the next one.